situation. Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it. It's therefore not unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then how can you say it's likely, that it's unlikely? Well, that's the way, that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the results of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence. It's just more likely, that's all. And it's a good guess. And we always try to guess the most likely explanation, keeping in the back of the mind the fact that if it doesn't work, then we must discuss the other possibilities. There was, for instance, for a while a phenomenon called superconductivity. There still is the phenomenon, which is that metals conduct electricity without resistance at low temperatures, and it was not at first obvious that this was a consequence of the known laws with these particles, but it turns out that it has been thought through carefully enough, and it's seen in fact to be a consequence of known laws. There are other phenomena, such as extrasensory perception, which cannot be explained by this known knowledge of physics here, and it is interesting, however, that phenomenon has not been well established, and that we cannot guarantee that it's there. So if it could be demonstrated, of course that would prove that the physics is incomplete, and therefore it's extremely interesting to physicists, whether it's right or wrong, and many, many experiments exist which show it doesn't work. The same goes for astrological influences. If it were true that the stars could affect the day that it was good to go to the dentist, then, as in America we have that kind of astrology, then it would be wrong, the physics theory would be wrong, because there's no mechanism understandable in principle from these things that would make it go. And that's the reason that there's some skepticism among scientists with regard to those ideas. Now you see, of course, that with this method we can disprove any definite theory. You have a definite theory, a real guess from which you can really compute consequences which could be compared to experiment, and in principle we can get rid of any theory. We can always prove any definite theory wrong. Notice, however, we never prove it right. Suppose that you invent a good guess, calculate the consequences, and discover that every consequence that you calculate agrees with experiment. The theory is then right? No, it is simply not proved wrong. Because in the future, there could be a wider range of experiments, you can compute a wider range of consequences, and you may discover then that the thing is wrong. That's why laws like Newton's laws for the motion of planets last such a long time. He guessed the law of gravitation, calculated all the kinds of consequences for the solar system and so on, compared them to experiment, and it took several hundred years before the slight error of the motion of Mercury was developed. During all that time, the theory had been failed to be proved wrong and could be taken to be temporarily right, but it can never be proved right, because tomorrow's experiment may succeed in proving what you thought was right wrong. So we never are right. We can only be sure we're wrong. However, it's rather remarkable that we can last so long. I mean, have some idea which will last so long. I must also point out to you that you cannot prove a vague theory wrong. If the guess that you make is poorly expressed and rather vague, and the method that you use for figuring out the consequences is rather a little vague, you're not sure, I mean, you say, I think everything's because it's all due to Mughals, and Mughals do this and that more or less, so I can sort of explain how this works, then you see that that theory is good because it can't be proved wrong. If the process of computing the consequences is indefinite, then with a little skill, any experimental result can be made to look like an expected consequence. You're probably familiar with that in other fields. For example, A hates his mother. The reason is, of course, because she didn't caress him or love him enough when he was a child. Actually, if you investigate, you find out that, as a matter of fact, he did love him very much and everything was all right. Well, then, it's because she was overindulgent when he was a child. So by having a vague theory, it's possible to get either result. Now, wait. Now, the cure for this one is the following. It would be possible to say, if it were possible to state ahead of time how much love is not enough and how much love is overindulgent exactly, and then there would be a perfectly legitimate theory against which you can make tests. It is usually said when this is pointed out, how much love is and so on, oh, you're dealing with psychological matters and things can't be defined so precisely. Yes, but then you can't claim to know anything about it. Now, I want to concentrate from now on, because I'm a theoretical physicist, I'm more delighted with this end of the problem, as to what goes, or how do you make the guesses. Now, it's strictly, as I said before, not of any importance where the guess comes from. It's only important that it should agree with experiment, and that it should be definite as definite as possible. What you say then is very simple. We've set up a machine, a great computing machine, which has a random wheel in it that makes a succession of guesses. And each time it guesses a hypothesis about how nature should work, computes immediately the consequences, and makes a comparison to a list of experimental results that it has at the other end. In other words, guessing is a dumb man's job. Actually, it's quite the opposite, and I will try to explain why. The first problem is how to start. You see, I'll start with all the known principles, but the principles that are all known are inconsistent with each other, so something has to be removed. So we get a lot of letters from people. We're always getting letters from people who are insisting that we ought to make holes in our guesses as follows. You see, you make a hole to make room for a new guess. Somebody says to you, people always say space is continuous, but how do you know when you get to a small enough dimension that there really are enough points in between? It isn't just a lot of dots separated by little distances. Or they say, you know those quantum mechanical amplitudes that you told me about, they're so complicated and absurd. What makes you think those are right? Maybe they aren't right. I get a lot of letters with such content, but I must say that such remarks are perfectly obvious and are perfectly clear to anybody who's working on this problem, and it doesn't do any good to point this out. The problem is not what might be wrong, but what might be substituted precisely in place of it. If you say anything precise, for example, in the case of a continuous space, suppose the precise proposition is that space really consists of a series of dots only, and the space between them doesn't mean anything, and the dots are in a cubic array. Then we can prove that immediately is wrong. That doesn't work. You see, the problem is not to change or to say something might be wrong, but to replace it by something, and that is not so easy. As soon as any real, definite idea is substituted, it becomes almost immediately apparent that it doesn't work. Secondly, there's an infinite number of possibilities of these simple types. It's something like this. You're sitting working very hard, you work for a long time trying to open a safe, and some Joe comes along who doesn't know anything about what you're doing or anything except that you're trying to open a safe. He says, you know, why don't you try the combination 10, 20, 30? Because you're busy, you're trying a lot of things. Maybe you already tried 10, 20, 30. Maybe you know that the middle number is already 32 and not 20. Maybe you know that, as a matter of fact, this is a 5-digit combination. There we have. So these letters don't do any good, and so please don't send me any letters trying to tell me how the thing is going to work. I read them to make sure that I haven't already thought of that. But it takes too long to answer them because they usually in the class try 10, 20, 30.